Okay, so in this video, we are going to sketch a graph of the function y equals x squared times e to the x. Remember the graph of the simpler function y equals e to the x? The graph looks something like this, because e is roughly 2.71828, e to the 0 is 1, e is always increasing, and the three key facts are e to the x is always strictly bigger than 0 for any given value of x. As x goes to positive infinity, y being e to the x goes to positive infinity, but as x goes to negative infinity, y actually approaches the x-axis, therefore y approaches 0. So as x goes to negative infinity, e to the x is getting closer and closer and closer to 0. Okay, so as always, now to sketch a graph of a function, all we really need are the first and second derivative. So y prime equals, we have here a product. This is x squared times e to the x, so we use the product rule. Derivative of the first function is 2x times the second function plus the first function x squared times the derivative of the second function, which is itself e to the x. We can factor an e to the x and an x, so this will end up being x e to the x times, and if you factor this out, if you take away an x e to the x from the first term, you're left with a 2. And if you take away an e to the x, you're left here with an x. So you're left with quite simply x plus 2. Now this is the factored form. When we find the second derivative, the idea will be to use this form to save ourselves one product rule. We'll multiply the x with this one, and so we'll have x squared plus 2x times e to the x. And this will be to help us find the second derivative in a little less work. Let's differentiate now with a single product rule. Derivative of the first function is 2x plus 2 times the second function e to the x plus the first function x squared plus 2x times the derivative of the second function, which is itself. Well, let's see what we can factor from this. If we factor a e to the x, we will be left with a 2x plus 2 with the first term, plus an x squared plus 2x for the second term. If we simplify, and I'll write the quadratic first, we'll have x squared plus 2x plus 2x is 4x plus 2 times, of course, the exponential e to the x. So we have found our first derivative factored and our second derivative factored. Well, sort of, this is a quadratic, and we know that our next step will be to find the critical points and the inflection points. But because the first and second derivative are always defined, we are going to look for values of x that make the first derivative 0 and the second derivative 0. So we'll obviously look for this quadratic and see if we can factor or not. So let's do it right away. If you look at this quadratic, you will not be able to factor by inspection because the roots are a little stranger. So we fall back on the quadratic formula. This will be equal to 0 if and only if, by the quadratic formula, x is negative b, so negative 4, plus or minus the square root of b squared, which is 16, minus 4ac, so minus 8. 16 minus 8 is just 8, and I will write here 8 as 2 times 4 to simplify the square root, over 2 times a is 1, so it's just over 2. Let us clean this up a little bit. I'll keep going here. Negative 4 plus or minus. Now the root of AB is the root of A root of B. So it's root of 2, root of 4 over 2. But root of 4 is just 2. So 4 over 2 is 2, so we get negative 2. Plus or minus. Root of 4 is 2 over 2 is 1, so plus or minus root 2. So we have found the two zeros of the second derivative. And now let's look at the zeros, the y-intercept, the critical, and inflection points. We already did here part of the work. So let's look for possible zeros of this function. How can our function y be equal to 0? The function is x squared times e to the x. So we have a product, but e to the x is always strictly positive. This term will never be 0. So the only way for y to be 0 is if x squared is 0, and x squared is 0 only when x is 0. So we have a single 0 of this function being x is equal to 0. And this also gives us the y-intercept. When x is 0, y is also equal to 0. So we can jump now to the critical points. As we have said, the derivative is always defined. So the only way to have a critical point is if the derivative is equal to 0. Well, the derivative y prime is equal to, in its factored form, x times x plus 2 times e to the x, and this will be 0 if and only if, well, again, we have a product. This times this times this, and a product is 0 if one of the factors is equal to 0. Therefore, if x is equal to 0, first critical point, x plus 2 is 0 if x is negative 2. E to the x is always strictly positive, so we only have two critical points where the derivative is 0. So at x equals 0 and negative 2, the curve will be flat at those 2 points. Possible inflection points now. And again, the second derivative is always defined. So the only way to have an inflection point is for the second derivative to be 0. So y double prime equals 0. But we already solved for this, right? We were trying to factor this quadratic, so we found its zeros. And we found that because e to the x is always strictly positive, the only way for the second derivative to be 0 is if its quadratic factor is equal to 0. And this is only possible if x is either negative 2, negative root 2, or x is negative 2, positive root 2. And so we have our two possible inflection points, our two critical points, and our 0. As always, our next move is to look for the classification of critical points. One thing worth mentioning, in the case of vertical asymptotes, a vertical asymptote is a point where the function blows up, but x squared is always defined, e to the x is always defined, so there is no single fixed value of x where the function will be undefined by blowing up, so we have here no vertical asymptotes. Let us now classify our two critical points. So let us look at classifying x equals 0. And again, to classify a critical point, we look at the second derivative at this point. So let's see. This right here is the second derivative. E to the 0 is 1. And we get 0, 0, 2. 2 times 1 is 2. So the second derivative at x equals 0 equals 2. We don't get it's 2, but that it is positive. Therefore, the curve is concave up at x equals 0. And because x equals 0 is a point where the derivative is 0, the curve will be flat there and concave up. Therefore, we have a local minimum. So you can imagine that the curve will look something like this. At x equals 0, well, we know the value of y is 0, so here we can be a little accurate. And the curve is concave up, and because at x equals 0 the derivative is equal to 0, it will be concave up and flat, so it has to be a local minimum. So around x equals 0, the function will look something like this. Let's classify our second critical point when x is negative 2. And again, all we need is the second derivative at negative 2. Hopefully it will be positive or negative. So let's see. This is again our second derivative. Plug in negative 2 here, what do you have? Negative 2 squared is 4, plus 2 is 6, minus 8, that's negative 2 times e to the negative 2. So we get negative 2 times e to the negative 2. Well, e to the negative 2 is positive, this is negative, so the whole thing is negative. Therefore, the curve is concave down at x equals negative 2. But if the curve is concave down, and at negative 2, we know that the derivative is equal to 0, so the curve will be flat and concave down at that point, so we have to have a local maximum. So, around x equals negative 2, suppose that the y value is here, the curve is concave down, so we have a local maximum. So it will look something like this. So we have classified successfully our two critical points. X equals 0 is a local minimum, x equals negative 2 is a local maximum, and those were our only two critical points, so we are now ready to look at a table of values. Let me actually use a little bit more space. You'll see why in a second, because we have these kind of nasty values with negative 2 plus root 2, negative 2, negative root 2, so we'll need to approximate those. Let me give myself a little bit more space. Okay, the first value we found was r0, when x is 0, y was 0. X equals 0 was also a local minimum. Then we found our two critical points, namely x equals 0 and x equals negative 2. Recall the function was y equals x squared, e to the x. And if you evaluate this at negative 2, here you will need your calculator, and you will find a value that is approximately 0.54. That takes care of our two critical points. The other two key points for this function were inflection points, namely negative 2 plus root of 2. And if you compute this, negative 2 plus root of 2, you will have an approximate value of negative 0.59. And if you compute this in here, so you replace x by negative 2 plus root 2, you'll have an approximate y value of 0.19. This was our first possible inflection point. The other was negative 2, negative root 2. And if you compute this with your calculator, you will find an approximate value of negative 3.41. And if you plug this in for x in the function, you will find a y value that is approximately 0.38. And now we have our table of values, at least initially for the 4 points of interest, the 2 critical and the 2 possible inflection points. We are now ready to produce an accurate sketch of our function. Keep in mind that x squared is always non-negative, e to the x is always strictly positive, so the y values can never be less than 0. And if you look at our y values, or x values, sorry, the points of interest are all negative except for 0. So most of our graph, the interesting features will be for negative values. So we can start here with our y-axis. So let's see, what are the points of interest? There's a point 0, 0 here. And once again, the picture does not have to be up to scale. The axes don't have to be up to scale, as long as the points are in the right position with respect to one another. So let's see, we have the point along x negative 2, roughly negative 0.6, and roughly negative 3.4. So we'll go on our x-axis around negative 4, negative 5. So negative 1, say, negative 2, negative 3, negative 4, negative 5. And suppose this is positive 1. Then for the y-axis, well, what is the range of our y values? The y values range from 0, 0.54, 0.19, 0.38. So suppose this is, we go up to about 0.54. So let's go in slices of 0.1. So 0.1, 0.2, 0.3, a little too big, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. And now let's plot our 4 points. The first point was easy, 0, 0. The second point of interest was negative 2, roughly 0.54. So it's almost 0.55. It's going to be about here. Then we had the point roughly negative 0.6. This would be negative 0.5, roughly negative 0.6. And the y value is 0.19, almost 0.2. And our fourth key point, x was roughly negative 3.4. So it's about here. And y is about 0.38, so it's almost here. So it's about here. Roughly negative 3.4 for x, and roughly 0.38 for y. So we have our 4 points. Now, as always, we first look locally around each critical point and complete the graph. If you go back to our classification, we knew around x equals 0, the graph looks like this. It was a local minimum. And around x equals negative 2, the graph looks like this because we had a local maximum. So let's glue this part onto the point x equals 0 of our graph, and this part onto the point x equals -2 of our graph. So x equals 0, local minimum. And then x equals -2, local maximum. And those were the only two critical points. So now we will try and piece these up together. If you look beyond x equals 0, there are no critical or inflection points, so the curve will never change its behavior again. Since it is increasing and concave up, it will be increasing and concave up forever. The question is, what will happen to y as x goes to positive infinity? Let's find this right away and see if we do have a right horizontal asymptote. So we look for the limit as x goes to infinity of y, but y was simply x squared e to the x. And as x goes to infinity, x squared goes to infinity, e to the x goes to infinity, so the whole product goes to infinity. So we do not have here a right horizontal asymptote. As x blows up to positive infinity, y also blows up to positive infinity. So we now have captured perfectly the behavior of our function from 0 to positive infinity. The curve will keep, I'll make this a little smoother, will keep increasing and being concave up, and the values will be getting larger and larger and larger up to infinity. And this will never change again because beyond x equals 0, there are no critical or inflection points. Let's now figure out what's happening here. Well, this point right here, x being roughly -0.6, this was, if you remember, one of our possible inflection points. Right? The two possible inflection points were -2 plus root 2, -2, root 2. The question is this a real inflection point? Well, let's see. To the right of this value, the curve is concave up. To the left of this value, we know the curve is concave down. So the curve is concave down. Here it's concave up. So obviously there is a change in concavity. And a function can only experience a change in concavity if you go through a possible inflection point. So this is a real inflection point. Curve is concave down. We hit the possible inflection point, which we know is a real inflection point, and as soon as we hit this point, -2 plus root 2, the curve switches to concave up. Now, what about this point? Well, this was our second possible inflection point. To the right, the curve is concave down. To the left, if you notice, we have no information. Is the curve concave up or concave down? We don't know. So here we'll verify the second derivative at, say, -4 to see whether or not the curve is concave up or down to the left of our other possible inflection point. So let's check this. We look for the second derivative at -4, and we can look at any value of x beyond -2, root 2 to the left, because we know that beyond this point there are no other possible inflection points. So the curve will always be of the same concavity to the left of this point. So any point would do. We could have looked at -4, sorry, -5, -6, -1000. The concavity will always remain the same to the left of this point. So let's check. Our second derivative, if you recall, was given by x squared plus 4x plus 2 times e to the x. And we now are trying to evaluate this at x equals -4. Well, let's see what we get. -4 squared is 16. 4 times negative 4 is negative 16, so these two cancel, and you're left with 2 times e to the negative 4, but e to any real number is positive, so this is positive. And you don't need to evaluate this because we don't care what the value of the second derivative is. We only care about whether it is positive or negative. Since the second derivative at negative 4 is positive, the curve around negative 4 will be concave up. And let's see if that's interesting. We know at negative 4 the curve is concave up. Let's go back to our graph now. At negative 4, the curve is concave up. So the curve will always be concave up to the left of this point. But if we look to the right, we know the curve is concave down. So this is indeed a real inflection point. So the curve will be concave down, 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 and then we hit this point. And we know beyond this point, since at negative 4 we have concave up, and the curve can only change its concavity at a possible inflection point. And here, this is a real inflection point. So the curve will go from concave down to concave up. The only question left over is what happens to the function beyond this point, say negative 4. What happens to y as x goes to negative infinity? Because we know beyond this point, the curve will never ever change its behavior. Beyond negative 2 root 2, negative 2 negative root 2, there are no inflection point, no critical points, therefore the curve will never change its behavior again. So you see it is increasing in concave up, it will be increasing concave up forever. The question is though, do we have a left horizontal asymptote? Well, let's see. What is the limit as x goes to negative infinity of y? Well, y was equal to, if you just go back, the function is x squared e to the x. So we have x squared times e to the x. Let's look at our case. As x goes to negative infinity, x squared, since 2 is even, goes to positive infinity. And if you look back to the graph of e to the x, as x goes to negative infinity, e to the x approaches 0. So e to the x approaches 0 when x goes to negative infinity. So this will approach 0, and we have an infinity times 0 case, which is a non-trivial case, because we have something really, really big times something really small. Which term will take over? Well, if you remember here, we can turn this into a either 0 over 0 or infinity case if we send one of these terms down, and we'll send the e to the x down, and this will become the limit as x goes to negative infinity of x squared stays on the numerator. If we send e to the x down, it will become e to the negative x. Let's look at our case now. As x goes to negative infinity, x squared goes to positive infinity. As x goes to negative infinity, negative x goes to positive infinity, and e to the positive infinity will give you positive infinity. So we still have an indeterminate case, but there's something interesting here. It is an infinity over infinity case, so we can try to use L'Hopital's rule. We are still letting x approach negative infinity, and recall that we replace the numerator by its derivative, and the denominator by its derivative. By the chain rule, we get negative e to the negative x. Let's look once again at our case. As x goes to negative infinity, 2x goes to negative infinity as well. E to the negative x, as we knew, goes to positive infinity. There's a negative up front. This goes to negative infinity. Once again, an indeterminate case, but we can use L'Hopital's rule one more time. the derivative of 2x is 2, over, by the chain rule here, you'll get back to e to the negative x. Look at our case, 2 is always 2, and as x goes to negative infinity, we know that e to the negative x goes to positive infinity. And of course, as you divide 2 by something which is getting bigger and bigger and bigger, the fraction is getting smaller and smaller and smaller and approaches 0. So the limit is exactly equal to 0. And so this is the first time that we encounter a horizontal asymptote. As x approaches negative infinity, y approaches 0. So y equals 0 is a left horizontal asymptote. And then we can go back and complete the graph of our function. As x is getting larger and larger negatively, y will be getting closer and closer to 0. And here I can tweak the curve a little bit to make it slightly steeper to approach 0 a little sooner, just to emphasize that we know that when x is getting larger and larger and larger negatively, the y values will be approaching 0. So I'll just tweak this a little bit and say it goes like this. So it is concave up and increasing, but as we have just said, as x becomes bigger and bigger and bigger negatively, y will be approaching 0. And now we have an accurate sketch of the function x squared e to the x. So let's see what we have in the end to label our points of interest. If you notice, x equals 0 was initially a local minimum as a critical point, but you can see the function is always strictly positive and is equal to 0 only when x is 0. So not only is this point a local minimum, it is a global minimum. Then we had the other critical point, x equals negative 2, and we knew that it was concave down at negative 2, therefore we had a local maximum. If you only look for values of x around negative 2, y attains its maximum value at x equals negative 2. So this is a local maximum. Is it a global maximum? Clearly not, because as you take larger x values, you will attain y values are much greater than this one. So this only is a local maximum, not a global maximum. And we had two possible inflection points. Are they real inflection points? Well, let's see. The curve went from concave down to concave up. So the point negative 2 plus root 2 is a real inflection point. And the point x equals negative 2 negative root 2, the curve goes from concave up to concave down. So both are real inflection points. And lastly, we have no vertical asymptotes, but we do have a left horizontal asymptote, and y is equal to 0. So we know that as x approaches negative infinity, y will be approaching the x-axis where the y value is 0. So the curve will be getting closer and closer to the x-axis where y is 0 as we keep moving further and further away to the left. And now we have sketched very accurately the function x squared e to the x using our first and second derivative. And once again, I don't think you could have guessed that the graph of x squared e to the x would look like this, with a global min a local max here, and 2 inflection points, and a left horizontal asymptote of y being equal to 0. We have again a highly non-trivial graph, but with the help of our first two derivatives, it wasn't too bad.